All right, guys, last day, 2 more pages. We got this. All right, so yesterday we were talking about gravitational potential energy, and we talked about how if we have two objects and they're at a large separation, then we have a new formula. We're going to say that the gravitational potential energy is equal to negative g, mass of the one object, mass of the other object, over r. This is a change from our original gravitational potential energy, where we used to just say that the gravitational potential energy is equal to mgh, where h is how far away we are from the surface of the Earth, and g is, of course, our 9.8. So we're going to use both of these potential energy functions to solve the same problem to figure out, well, how good is this approximation near the surface of the Earth? Do both of them give the same answer? We are going to say, let's use the conservation of energy to find the speed v. The instant before a mass m hits the surface of the Earth dropped from a height of 1,000 meters. So on the left, we're going to use our old potential energy function, and we can say, all right, our kinetic initial plus potential initial is going to equal kinetic final plus potential final. And we can simplify this a little bit because we know that we are starting from rest, so there's no initial kinetic energy. And when we hit the surface of the Earth, y is 0, so there's no potential energy final. So we've got mgh is going to equal 1/2 mv squared. Yay, look at that. Mass cancels. That's why they didn't even need to tell it to you. So all we can say is that if we take 9.8 times 1,000, set that equal to 1/2 v squared, and solve for the speed, we are going to get 140 meters per second. Yay! Nice, straightforward. However, the assumption that we're making here is that g is constant, 9.8, throughout the whole thing, and we know that that's not true. As we get further away from the surface of the Earth, our acceleration due to gravity will decrease. So this is not the most accurate way to do it, but let's see just how close to the answer we get if we do it the other way. So we're going to use our gravitational potential energy, negative g, mass of the Earth, mass of the object, over r. We're going to start setting up the same way. Kinetic energy initial plus potential energy initial is going to equal kinetic energy final plus potential energy final. But what are we going to cross off here? Well, we're still starting from rest. The initial potential energy, we're at a height of 1,000 meters, so we have potential energy. Right before it lands, we're moving, so it's still got kinetic, and we still have potential energy final. We're not at 0 here. We're at the radius of the Earth. So what we can say is that we're starting negative g, mass of the Earth, mass of the object, at a height of the radius of the Earth plus 1,000. That's going to equal 1/2 mv squared, and we're ending with the potential energy, well, it's plus negative. That just erased so much. I put it back. Plus, I'll just write a negative sign here, plus negative g, mass of the Earth, mass of the object, over here, we're just at the radius of the Earth. So it's definitely uglier, but I know all these values. So I know it's negative 6.67 times 10 to the negative 11th times the mass of the Earth. Whoops, sliding. I'm struggling today. 5.97 times 10 to the 24th over raise the Earth, 6.38 times 10 to the 6th plus 1,000. You'll notice I left out the little mass because technically that's in every term, so I can cancel that. I'll do that right there for you guys. So that's going to equal 1/2 v squared minus, I'm going to write it down here because I am out of space, minus 6.67 times 10 to the negative 11th times the mass of the Earth, 5.97, I'm still running out of space, times 10 to the 24th. You guys hopefully can see that. Divided by just the radius of the Earth, which is 6.38 times 10 to the 6th. All right, not my neatest handwriting. Hopefully you can follow all that. I'll come down over here. When you calculate that out, you should get 139.865 meters per second. Hey, that's pretty close. How close is that? We can figure out what the actual percent difference is. Percent difference. We can say it's the absolute value of our 139.865 minus 140 divided by 139.865 times 100. So the percent difference here is actually 0.00096%. So it's a pretty good approximation, MGH. MGH works pretty well. As our H gets larger and larger and larger, you can see in the picture to your left the difference between the MGH function and your negative GMM over R function gets larger and larger and larger. But when we're down here, they're pretty close. And we get more different, more different, more different, and you get way more of a difference. When we are at large R's, obviously you want to use part B. You want to do it this way. If you're near the surface of the Earth, of course, simplify it and make it the easier way. All right, last page. What? Crazy. There's not even too much on this page. We're going to talk about the energy of an orbiting satellite. All right, so we know satellites, when they're orbiting, they're traveling in circular motion. So the centripetal or radial force is the force that's causing it to go in the circle, which is our force of gravity. So we can say mv squared over r is going to equal g, mass of the Earth, mass of the object, over r squared. Well, this r cancels with that squared, and what we have is mv squared is therefore g, mass of the Earth, mass of the object. In this case, it's a satellite, so I'll throw an S there. I can throw an S here too, over R. Well, I want to think real quick about the kinetic energy of our satellite. The kinetic energy of anything is 1/2 mv squared. So if we're talking about the kinetic energy of the satellite, it's 1/2 mass of the satellite times v squared. Well, mv squared, we just found out, is g, mass of the Earth, mass of the satellite, over r. So let's plug that in. The kinetic energy of the satellite is therefore 1/2 of g, mass of the Earth, mass of the satellite, over r. Well, this right here is the absolute value of the potential energy for satellite. Hopefully that looked familiar. That's what we derived. That's what we've been using. So we can actually say that the kinetic energy of a satellite is 1/2 of the absolute value of the potential energy of a satellite. What? Crazy. This will always be true. Little fun fact that can help you solve some problems sometimes. Always true. I missed a Y. Always true. Yay! That's the last page. Woohoo! Of course, if you guys have questions, if anything doesn't make sense, let me know. I can go talk more in detail. Hopefully you guys have an awesome day, and I will talk to you soon.